those off. That's that. We can go back here. Still chapter 4. We'll be chapter 4 for, especially because we don't have class Tuesday, probably the next 2 weeks. By the time we go through everything in chapter 4. Yeah, probably. So last time, if I'm not mistaken, we talked about ionic bonding. Okay, and we started talking about it, where you've got a transfer of electrons from one atom to the other. Do we remember this? Yes, okay. And in ionic bonding, then, because we've got that transfer, ions are created. You have the cations and anions, and they bond together or stick together because of those charges. One's a positive charge, one's a negative charge. And we talked about salt, how it forms in this regular pattern as it goes through, and it gets more complex as you get off the 1-to-1 ratios. So what I want to do now is I want to jump back a little bit and work some examples. A lot of chapter 4 is going to actually be working examples and so forth, but using the dot diagram to predict a formula. So if I start with sodium, I'm going to have 1 dot on my sodium atom, and the chlorine is going to have 7 dots with it. So it looks like this. So this is what our elemental dot diagrams look like. Does that ring a bell for everyone? On the same page there? Okay. So now the octet rule says that atoms want to either get to 8 or 0, basically, in terms of their valence electrons. So we can very easily see that sodium would be happy to donate its electron, and it becomes a sodium plus with no valence electron, so it's happy in terms of the octet rule. Chlorine then takes that valence electron to get to 8, and it forms a minus. So now sodium is happy, chlorine is happy, and it ends up forming the compound NaCl. Everyone's happy? That's our compound that forms, NaCl. So both atoms have fulfilled the octet rule, so everything's good, and that's the compound that forms. And in real life, that's what happens. That's exactly what happens. You have 1 sodium reacting with 1 chlorine. But what happens if it's not as simple as 1-to-1? Let's say, for example, we have sodium with this 1 valence electron, and sulfur which has 8 valence electrons. So now when these two react together, sodium says, okay, great. You'll take an electron, I'll give 1 up. So sodium gives up 1 valence electron. So sodium is now happy because it's given up all of its electrons, but sulfur only has 7. So what sulfur is going to do is it's going to say, okay, look, it's never just 1 atom and 1 atom reacting together. You can't do that because they're so incredibly small. You're always moving billions and billions of these atoms together when it comes in contact with one another. So since there's a lot more sodiums around, I'm just going to find another one. And when I find that one, I'm going to take that electron as well. So the second sodium gives up its electron to fulfill the octet rule for this sodium. Sulfur then now, since it's taken 2, has 2, 4, 6, 8, and it's fulfilled the octet rule as well. So when sodium and sulfur react, it ends up forming the compound Na2S. Na2. It takes 2 sodiums for every sulfur. And when you do this in the lab, this is exactly what you see as well. You get a 2-to-1 ratio here. And you know it works out, first because you accounted for all the valence electrons in the octet rule. Also, if you look at the charges, sodium is a +1, and I have 2 of them. So that's going to be a +2 overall. Sulfur is a -2 overall, so those charges are going to balance out one another. So +2 plus a -2 goes to 0, so our charge is balanced. In any compound, the charges are always going to balance out to 0. Any compound, that's true. We'll learn about an exception later, but it's not really a compound. So this compound can be explained by the octet rule by simply moving our electrons around. Let's have you guys give one a try. Let's say that I want the reaction between, let's not do that. Let's do aluminum and chlorine. So using dot diagrams, see if you can predict what compound would form when aluminum reacts with chlorine. Aluminum is number 13 on the periodic table in the 3rd column. Chlorine is 17 in the 7th column. Say 30 seconds or so. Okay. Anyone need more time? So here we are then. I'm going to say something else, but I feel kind of stupid about this. As you notice, the room is significantly emptier than it was on exam day. And this is silly for me to tell you because you are the one showing up for class. But just in case you're thinking about skipping class, the stuff we're doing right now is going to be used like through the rest of the course. Okay, so don't skip, if that makes sense. If you have to skip, don't choose right now to skip. I'm not sure how to say that. But in the past, a lot of the stuff was review and so forth, and that's fine. But now, oftentimes it's new for a lot of students and so forth, and we're going to start building upon it over and over again. So it's just not a good time. That's what I'm trying to say, if that makes sense. Okay. Aluminum and chlorine. And again, I feel stupid saying that because you guys are actually the ones here, and so forth. Aluminum is going to have 3 valence electrons. Chlorine is going to have 7 valence electrons. Everyone understand where that comes from? Okay. So now aluminum wants to give up 3, chlorine wants to take 1. So here we go. Aluminum gives up 1, chlorine now is happy with the octet rule. So it doesn't want any more, but aluminum still has 2 more left to go. So it's going to find another chlorine, donate that one, and then finally 1 more chlorine to bring that one over there. Okay, so now the aluminum is happy with the octet rule, chlorine is happy with the octet rule. If we look at the formula, it's going to be AlCl3. AlCl3, yeah.
do we not put the charges in there? Because I have, well, does it matter what order to? Because I put CL with a -1 charge, 3, AL, +3 charge.
Okay.
So is that still right or no?
As far as I'm concerned, it's right.
Okay.
You did the work and you did it correctly, so it's right. Normally, we list the metal first,
Oh, okay.
and then the non-metal. We haven't talked about that at all. So when we're listing it, whichever element is furthest to the left on the periodic table is listed first.
Okay.
Then the one on the right, as if you're reading across. So like if you're going across, it's aluminum and then chlorine's like after it. So that's how I
So
think of it.
we don't have to put the charge either though?
You don't really have to put a charge because the charge is always there. So aluminum is always +3, chlorine is always -1. So in those cases, we don't have to worry about a charge because they're just understood to be there.
Okay.
Like you don't have to write the 1 there because of the fact that you've got 1.
Right, okay.
Okay. One second. Yeah.
So you just basically repeat the process over again. So you ditched 1 from the aluminum. That fulfilled that. However, you still got 2 more, so you just, once again, assume chlorine has 7 again, give another one,
Yep.
7 again, give another one, until that aluminum
Until-
is purged.
Till everyone's happy with octet roll.
Okay.
Yep. Mhm.
So, the subscripts, the numbers on the CL3,
Yeah.
basically that is dependent on how many times you use that element.
Exactly.
Okay.
Mhm. So this molecule or this compound is going to be made up of 1 aluminum and 3 chlorines each time.
Okay.
Any other questions? Yeah.
Oh yeah, so that one I get, but the other one we just did, the Na2S2 minus, why is it all those numbers? I know it's Na2 because we use 2 NAs, but what is the 2 negative for?
Okay, so all I'm doing there is, you can put them on there, absolutely, it's not a problem. Okay, so like, over here, if you wrote +3 -1, that's okay, and that's what you were asking. It's perfectly fine. All I was doing there, though, is showing that the charges balance out, because you have 2 +1s to give you a +2, and a -2 balances out to be 0. Over here, you would have a +3 times a -1, which again adds up to 0. That's all I was doing, is
Like,
just
you
showing
have
that
to
the
add
charge
negatives
balance.
to the,
You don't have to write them,
Okay.
but I'm not going to count wrong if you do. I'm also not going to count wrong if you switch the order of them or anything like that. So, yeah. Yeah, really that's just convention for chemists, and it's like what we're used to, but so good. Okay, shall we try one more? Let's do. Okay, let's do this one. Let's do tin, which is going to give up its 4 electrons and oxygen. Because tin's in the 4th column, so I have to tell you that it is giving up its electrons. It's not bringing electrons in, it's giving them up. Say 30 seconds or so. Okay, does everyone have their idea? Okay, so tin, as I said, has 4 valence electrons to start with, and it's going to get rid of 4. So let's just start with 4 here. Oxygen has 6. So to fulfill the octet role, oxygen needs 2 more. So the first one's going to go over, and then the second one's going to go over. And then tin still has 2 more, so it's going to find another oxygen. Transfers over the last 2 there. So tin gives up all 4 to get to 0, so it's happy with the octet rule. Oxygen takes 2 twice, so they're both happy with the octet rule. Okay. Does that make sense? Okay, so the formula for this is going to be SnO2. SnO2. And this is really a very, very simple way to predict what's going to happen. And it's what happens in real life. If I take a piece of tin and I react it with oxygen, basically heat it up in oxygen, the compound that forms is SnO2. Exactly what happens. Predicted that way. So this is the easiest way to predict a formula. It's a bit cumbersome because you've got to draw everything out and so forth. So I'm going to show you a trick that you can use for predicting ionic compounds, and that's called, there's really no good name for it. A lot of people call it the crossover trick. I'm not sure where that comes from. Well, I guess I know where that comes from, but who came up with it or anything? But here's what you do. So you look at the 2 compounds you have. Let's do this one first. So I've got Na and I've got S. Na is in the first column of the periodic table. So when it goes into a compound, it's going to give up an electron and become a +1. Everything in that first column is going to become a +1. So if it's lithium, sodium, potassium, rubidium, it doesn't matter. They all become a +1 because they have 1 valence electron, they want to give that up. Sulfur is in the 6th column, so it needs to gain 2 electrons and become a -2. So sulfur starts out with 6, gains 2 more electrons, 2 negatives, and becomes a -2 because of that.
I have a question.
Yeah.
Anytime they're in the 4th column, do they automatically want to give them up, or do they want to gain?
50-50.
So
50-50.
does it matter, or does it depend on the element?
It depends on what it's paired with. As far as you're concerned, I will always tell you if it's giving them up or bringing them in, because
Okay.
it's not really fair for you guys to have to figure that out.
Okay.
It's not super hard, but it's just a little beyond the scope of the
Okay.
class. So I will always tell you that.
Okay, thank you.
The other ones, though, you should be able to figure out from the octet rule. Okay, so sodium is a +1, sulfur is a -2. Now the crossover trick is you take the number of the charge and you make it a subscript on the other atom. So the 1 from the sodium becomes a 1 after the S. The 2 on the sulfur becomes a 2 after the Na, which leads us to Na2S. Na2S. So the 1 here becomes a subscript, the 2 becomes a subscript, so you end up with 2 and a 1. And that's called the crossover trick. It works because what you're actually doing is balancing charges, but it's a very simple way to do it. And this works for ionic compounds.
And that's only if you give us the charges?
Well, that's if you figure out the charges.
Oh,
Okay. But once you get used to doing this, that's going to become relatively easy to do.
okay.
Everything in the first column is going to be a +1. Everything in the second column is going to become a +2. Everything in the third column is going to become a +3. Everything in this column is either +4 or -4. This becomes -3, -2, -1, and 0. So it basically counts up +1, +2, +3, +4. and then you count down. -3, -2, -1, and then 0. Alright, so if you can just remember that, it's the same thing. But you'll get the same answer if you draw out the dots and do the octet rule for it as well. Either way, it's just a shortcut for you. Okay, aluminum and chlorine. Do it over here. I know that computer was in the way before. Aluminum becomes a +3. Chlorine becomes a 1-. So then when you do the crossover trick, the 3 comes after the chlorine, the 1 after the aluminum, AlCl3. AlCl3, which is exactly the same thing we got by actually drawing it out and moving all of our electrons around. It's all in the same stuff. It's just a mathematical trick to kind of shortcut it for you.
Would you want to do this instead, or you want to do the dots?
I don't care what you do unless I specifically ask. So like on the exam, for example, there'll be probably one question saying, using dot diagrams show how to predict the formula. And then everything else will just be like predict the formula, and then you can do whatever you want. The reason I show the dots is because that really is what's happening. The electrons are being transferred and so forth. This is just a quick hand way to do it.
Now, is there a time when this method won't work?
Not as long as it's ionic.
Okay.
So as long as it's ionic, it's going to work. Yeah. Now, let's do the last one because I want to show you that one. 10s plus 4, oxygen is 2-. So when we bring those together, the 4 is going to come over here and the 2 is going to go there to give you SN2O4. SN2O4. Now, if you were to stop there, I would be perfectly fine with that. I've got no problems with it. Chemists normally are going to reduce it down because you can divide both of those by 2 to give you SNO2. But this is perfectly fine. That's perfectly fine. Either way, you end up with the same ratio, so I'm happy with it. But this is why you'll normally see it reduced down to the smallest numbers there. You guys think you got a grasp of this? Yeah.
When you reduce it down to the smallest number, you always take the last number and divide it by the first number, or the biggest by the smallest?
You're going to divide the biggest by the smallest.
Okay.
As long as they go into whole number ratios. Like if this was 3 and 4, then you couldn't reduce it down because 3 doesn't go into both of them.
Right.
But here, since it's 2 and 4, 2 divided by that would give you 1 and so forth. Like I said, it's again a convention. I don't particularly care if you do it or not, but in real life you'll see it like that way.
Okay.
Okay, so let's have you guys try one. Well, let's do carbon as a +4 and chlorine. Oh, wait, that's not going to work. Sorry. Lead as a +4 and chlorine. You should be able to figure out the charge of the chlorine. Let's say 20 seconds or so. So lead is a +4. What is chlorine? What charge does the chlorine take on when it goes into a compound? -1. -1. So then, to do the crossover trick, it's going to move over and over, and that's going to end up as PbCl4. PbCl4.
But once again, if we find it easier to do the diagram just to make,
Yep.
it's fine.
Yep, you can do the diagram to predict it. It's never wrong. It just takes more time.
So how is it that, like you said before in the first example, that you filled it with the rule of octet with 8, and then all of a sudden you're like, oh, we have 2 extra. It just found another one. So like, when you said it's just always around, what do you mean by like?
So when you do a reaction in the lab, okay, say I'm going to react aluminum with chlorine. I don't pick up an atom of aluminum and an atom of chlorine and put them next to each other, okay? Because they're so incredibly small, you can't do that. Okay? So what you do is you take a pile of aluminum and a pile of chlorine. Now inside those piles, like a pinch of aluminum, how many atoms are in there? I mean, billions and billions and billions of atoms. And same with chlorine. So there's always
Extra.
others for them to react with. Now, if I did just take 1 and 1, then this all falls apart.
That was what I was thinking originally.
It doesn't work that way, but because of the fact that you can't really do that ever, then you don't worry about it, because there's always more and more around. Yeah, we don't ever worry about like limiting. So if you were in high school and you learned about limiting reagents and so forth, that's not something we cover in this class. So we don't have to worry about that. I mean, yeah, you can go back to the Bohr model and work your way forward with this. I mean, if you don't, please. I mean, you could go back to how many protons, neutrons, and electrons are in aluminum and work your way forward. It's all building upon itself, which is why I was so happy to see your guys' exam scores. For the most part, everyone did good, very well in here. So you've got, hopefully, that groundwork that we can move forward from. Any questions about coming up with a formula for an ionic compound? Oh, I think most of you are looking fairly bored at this point, so it's usually a good sign. Now, naming ionic compounds. Naming of ionic compounds breaks down to 2 basic ideas. And really, the first one's kind of silly. So to name an ionic compound, the cation name stays the same. So this is the metal component. The metal component. So if I was to name aluminum and chlorine here, AlCl3, the cation is aluminum. So the name is going to start with aluminum. Very boring. Over here, SnO2 is going to be tin. PbCl4 is going to start out with lead. So the cation, the metal component, actually the first one listed generally, is going to stay the same. It's not going to change at all. The second part, the anion ending changes to an IDE. So you take the element's name, so for example, here is chlorine. And you're going to change the ending to an IDE. So we're going to get rid of this, and chlorine is going to become chloride. So AlCl3 is going to be aluminum chloride. Aluminum chloride. SnO2 is going to become tin, and oxygen is going to lose the ending and add an IDE and become oxide. So tin oxide. And over here again, we got chlorine. So it's going to become chloride. So aluminum chloride, tin oxide, lead chloride. First element's name stays the same. Second element's ending gets changed to an IDE. And that's really the extent of it.
Is that like when we're doing the dots, or just like in general?
In general, it's always true. So it doesn't matter how you get to it. There are 2 special cases we're going to talk about, but for now, this is just how we go about doing it. Okay. So let's have you guys try 1 or 2. How about CAS? Ca is calcium. S is sulfur. I know you guys don't have the names on the periodic table, so on your paper, see if you can come up with what the name would be for CAS. Okay. So the name for CAS, well, anyone feel brave and want to share? Okay.
Calcium sulfide?
Calcium sulfide, is that what you got?
That's what it is.
Yep, and that's correct. Calcium sulfide. Now, another thing for this class, and this class only, is the fact that if you look at chloride, chlorine actually lost 3 letters from the end. Sulfur only lost 2 letters. So you may not be sure how many letters to lose when you change the ending. So as long as something is lost and you put an IDE on the end, I'm happy with it. Now normally you're going to know them. So like if, for example, instead of sulfide you wrote sulfide, I would accept that. That's fine. Okay, now it probably sounds weird to you. If I go 1 letter further, sulfide, kind of sounds weird too. And so I'm okay with that. So as long as you're ending it in an IDE, that's what I care about. Because different elements, you are going to lose different amount of letters from the end there. Like oxygen. Oxygen, you lose all 4 to become oxide. But if you wrote it as oxygen, I'm okay with it. Okay? Again, you guys know these things. It's not like these are super rare words or anything. Oxide, if I say oxide to you, that sounds right. If I say oxygen, that doesn't sound right, right? Because in everyday life, you hear these terms and you know them. Sulfide just sounds right to you because that's something that you've heard before. Sulfides, oftentimes, one example is in wines. A lot of people have reactions to sulfides in wines and it gives them headaches. So you'll hear about sulfide content in wines and so forth because of that. Okay, so let's try another one. KBr, K, I need a handout here. Is potassium, Br is bromine. Everyone got their idea? Okay, this one is going to be potassium. Bromide. Potassium bromide. So going from a formula to a name, it's really just a matter of going through these two steps. Everyone good with that for now? What about the reverse? What if you actually have a name instead of a formula? So let's say that we start out with aluminum oxide. And I want to go to find the formula for this. This is actually a bit more complicated. This is probably the hardest part of naming in general. So what you're going to do is you're going to look and identify what elements are here. So we have aluminum and we have oxygen. That's not the hard part. I think everyone can figure out it's aluminum and oxygen. But the trick to this is you need to make sure that your charges balance out to 0. So aluminum is a +3, oxygen is a -2. So if I only have one of each, they don't balance out. So what we need to do is actually do our crossover trick here. And we find that aluminum oxide is actually Al2O3. Al2O3. So when you have ionic compounds, it doesn't tell you the number of each component that you have, so you have to look at it and make sure that your charges balance out. Does that kind of make sense? Want to give one a try? Okay. So let's try calcium fluoride. Calcium fluoride. Okay. Calcium fluoride, calcium is Ca, fluoride is fluorine, and that's F. So does CaF, one of each, balance out? No, they don't. Because what charge does calcium have in a compound? 2 plus. It's in the second column, so it's 2 plus. And what does fluorine have? -1. So when we bring those over, we end up with CaF2. CaF2. So this really is the hardest part of naming for students in the past. They can come up with what elements are part of it, but then they forget that they have to balance the charges because it's ionic. When we get to covalent, we don't have to worry about this, which I think adds to the problem. But when it's ionic, you do have to make sure that your charges balance out. So let's try one more. Let's do calcium sulfide.
When you were over there before, you were saying, just, I guess, try to memorize in your mind, negative, what, 5, 4, 3, 2, 1. Can you do that again?
Okay, yep. So this column here is +1, 2 is +2, this one is +3, this is +4 or -4, -3, -2, -1. So along with that, then calcium is going to be a +2. Sulfur is going to be a -2. So when we bring these together, you can use Ca2S2 or CaS. CaS. Is that what you got? Good. Good, good, good. Okay, then we're going to stop here for lecture today because I have to hand back the exams. Next time in class, we're going to learn about a couple add-ons to this. When we have a transition metal, we don't know the charge because the charges can be different, and then something called polyatomic ion. We'll pick up with that next time. I guess on Thursday. Okay, any last minute questions before